Okay, so welcome everyone. And this is the plenary session number 8. And we will have two talks. The first one is given by Dmitry Butker from Berkeley and Mainz. And he will talk about searching for ultra-large bosonic fields. So you have 30 plus 5 minutes. So you can start.
Thank you very much, Professor Kwan. And thank you to the organizers for the opportunity to speak here. Interestingly, there is a whole parallel conference currently going on, which is PATRAS, which is devoted to dark matter searches entirely. So there is really a lot of going on this week. Now, there used to be a time, believe it or not, when we met in person, and this picture that you see here was taken, I believe, in 2019, when I had a good chance to visit Daejeon in Korea, and you see some of the important players on this picture in the field of axions and axion searches. This is taken in a science park in Daejeon, and then you see here there is an elephant. And this one is an elephant kind of outside in the park. But the reason that we were there to discuss was actually an elephant in the room, so to say, which is that we have a big problem. Most of the matter that we see in the universe is apparently dark matter, and we don't know what it is. And to make things worse, there's actually many different elephants representing various kinds of mysteries in modern physics. Why is there matter and antimatter symmetry in the universe? Why do we have similar amounts of dark matter and normal matter? Why do strong interactions respect CP symmetry when QCD admits very nicely the violation of CP? Why is there hierarchy? Why, meaning that, for example, all the particle masses that we know are many orders of magnitude lighter than the natural scales of physics, such as grand unification scale or Planck scale. We're not going to touch the dark energy. And of course, intellectually appealing would be to say that, in fact, there's maybe one elephant, and all of these apparent elephants are just different aspects. So what we need to do urgently is to understand dark matter, for example, a little bit more the nature of dark matter. And the question arises, so what is dark matter, or maybe what is there that conspires so we think there is dark matter? And there are many possible things. Here is a long list of candidates. I'm going to show you to you right away in its entirety, so to say. And it starts with the suggestion that maybe it's not actually matter, but some kind of a misunderstanding of how gravity works at long distances, and theories like, for example, modified Newtonian dynamics are being put forward to that goal. And maybe still the most sort of popular explanation is that there are some weakly interactive massive particles that are very heavy but interact with the standard model particles very weakly, and that dark matter is them. This is sort of nowadays a conventional explanation. But unfortunately, the searches for WIMPs have not found them as yet, even though my understanding is that the parameter space is not yet closed for them. But nevertheless, I think partially motivated by the absence of the discovery of WIMPs here. In the last, I don't know, already maybe 10 years or so, another very prominent class of candidates came forward, and I would probably assess that this is the second most popular, I should say, I don't know best, worst, but the second most popular candidate, which can be grouped into this large general category of ultralight bosonic fields. And depending on the spin and parity of the underlying particles, they could be scalars, for example, like dilatons, or they could be pseudoscalar like axions, which have an additional benefit that they also solve the CP problems, combining at least two of the elephants together. And generally, axion-like particles that are also pseudoscalar particles but do not solve the CP problem. These could be also vector particles, for instance, dark and hidden photons, could be tensor particles. And so this is a broad category, and my talk will be mostly about searches for these things. I should mention here that there is a completely different paradigm to explain what dark matter is, and this is something that's being championed by Ariel Zhednitsky and others. And this is the paradigm of anti-quark nuggets, or axion quark nuggets, whatever you want to call them, but AQN is the common abbreviation. And here, dark matter is not actually a particle that interacts weakly. In fact, when one of these objects when one of these objects hits the Earth, it deposits the energy as it passes through the Earth, equal to perhaps a nuclear bomb explosion. But because it's like spread over the length of the Earth, actually nothing particularly terrible happens. And now you might ask how this dark matter, and the answer to this is that these are very dense objects, basically with nuclear density, and their cross-section to mass ratio is very small. And in fact, in astrophysics, that's what matters. So this is a completely different paradigm. These are very strongly interacting particles, but still could be dark matter. And there are interesting search efforts for that as well. Maybe I'll mention very briefly, but mostly I decided what I'm going to do today is I'm going to give you, maybe not going into too much detail, but I'll give you some general overview of these ultralight bosonic dark matter searches, and being a bit biased, telling you the things I'm mostly the things I'm involved with myself, but not exclusively. Anyway, starting this overview, I would like to say that we have a whole program looking for galactic fields associated with this bosonic dark matter using nuclear magnetic resonance technique. And this program goes by the name CASPER. It's Cosmic Axion Spin Precession Experiments. You know, if you think about how could, in principle, a pseudoscalar particle couple to standard model particles, you find that there are two interactions that are have been kind of overlooked initially. So people typically focus on the axion or ALP coupling to photons, and most experiments that we have, they look for that kind of coupling. But the other couplings, one of them is when instead of the photons, the axion field couples to gluons, and that gives, for example, a nucleus, an electric dipole moment that's proportional to the field, to this bosonic field that's present locally. Now, this field actually, due to the Klein-Gordon equation, it has to oscillate in time at a frequency that is given by the mass of the underlying particle. And so this electric dipole moment that the nucleus gets also oscillates in time. And this suggests immediately the way to look for it. So we do a rather traditional, in a way, conceptually traditional NMR experiment where we polarize nuclei along a magnetic field, and we apply a strong electric field in the perpendicular direction. And then if there is an oscillating dipole moment, this creates, from the point of view of nuclear spins, a small field that oscillates excuse me, this is okay, oscillates perpendicular to the main field, and when the frequency of this oscillation, which is again the mass of the axion, basically, when it matches the Larmor frequency, there is a resonance, and the spins prepared initially along the strong magnetic field, they get out of the plane and can be detected with the magnetometer. And this Caspar electric experiment operates currently at Boston University, and this part of the Caspar program is led by Alexander Sushkov, and we recently published a paper describing our results. A curious note about this paper is that in the PRL issue, it follows directly after the G-2 results. So if you go and read the G-2 paper, don't stop. Please read also our Caspar paper. So that's the EDM interaction of the axion, but another way the axion or ALP can interact with the bosonic, with the with the normal with the spins, let's say, is the so-called gradient interaction, and it's of the form now not the amplitude of the axion field, but the spatial gradient of the axion field, and it's dotted into the spin, and this looks basically like the axionic dark matter field creates a quasi-magnetic field background, and we can do a similar experiment which does not require now the electric field, and look for this effect. Sometimes it's called axion wind, but I think it's a bit of a misnomer. But anyway, we have an experiment that's looking for it in mines, and it's also producing results now, and has been cutting into the axion-like particle parameter space for now. Now, I should say that NMR is not the only way to look for these things. There are many kinds of spin-based sensors to look for dark matter, and there is a bit of an explosion. Currently, there are masers, there are spin amplifiers. So here I have a little picture of the apparatus that was put together by my colleagues at the Institute of Science and Technology in Hefei in China, and with this apparatus, it was possible to look for quite low frequency axion-like particles, and also very significantly cut into the unknown parameter space so far. Now, it's important to realize that while it is, of course, very important to look for galactic dark matter directly by trying to measure these fields that surround us, you can also search for dark matter particles indirectly. If they do exist, they should basically modify the way standard model particles interact with themselves, and cause various effects that sometimes are called the fifth force effects. And some of them are spin independent, but there are a lot of them that are also spin dependent, velocity dependent, etc. And so here you see a search in Hefei that also yielded some interesting results recently, which is basically very similar to this galactic dark matter search. Only here we have also a source, and this is an object that looks like a small helicopter that's positioned next to the sensing apparatus, and there is a mass that's moving around, and this is looking for spin velocity coupling, one of these possible interactions. And it's interesting because you can find these exotic particles with this method, even if they are not part of the galactic dark matter currently. Now, also, when people think about sort of the topology of dark matter, so basically like a fluctuating field without structure is one idea, maybe the simplest idea, but there are also a lot of ideas that dark matter can clump into objects of different dimensionality from zero, for example, axion stars or cue balls or something, to one, strings, to two, the main walls as shown in this cartoon over here. And so some years ago, we set up an experiment that's called Global Network of Optical Magnetometers for Exotic Physics Searches, and it consists of by now almost 24 stations all around the world, including in Korea. There is a station in Daejeon. It's very active, and I will show you maybe a little bit later how this works in a movie. But basically, when the main wall of dark matter crosses the Earth, we should see signals in various sensors with a predictable timing. And these sensors are all enclosed in magnetic shielding, so they shouldn't be sensitive to some kind of geomagnetic field perturbations. They only should be sensitive nominally only to these exotic fields that ignore the shielding. So we've been operating this for a few years, and the ideas actually got caught, and people started doing also clock networks. And clock networks are sensitive to scalar particles. And there are some very, very cute ones. For instance, people use the constellation of the GPS satellites, which all have atomic clocks on them, as a big Earth-size dark matter detector. And recently, partially motivated by some theoretical developments, specifically the development of the so-called relaxion theories, the hybrid networks are extremely well motivated. In these networks, you look for fields that could couple both to spins and to fundamental constants. This is what is behind the clock network. So now we actually have hybrid networks, and in fact, this GPS.dm network and Gnome, they have close collaboration, and now we cross-correlate the data. This network, by the way, doesn't really have to only search for galactic dark matter. It can also look for events that come from some highly intense occurrences in the universe, like supernova explosions or mergers. Now, let me mention another a bit of an exotic experiment, and there are actually several groups that independently pursued these in the last couple of years. And the idea here is that imagine that you have some object. Well, this is here suggestively drawn as a little elephant that is made out of something that interacts only very weakly with normal matter. But of course, it does interact gravitationally. And if somehow this object is formed to be trapped in the Earth gravitational field, it can undergo oscillations within the Earth, for example. Now, it so happens that geologists have set up an amazing network of gravimeters all around the planet, and these are really amazing instruments. They can measure, one of them can measure maybe small g to 10 to minus 12 per root hertz or something. This is really a remarkable network, and what's interesting is all their data are available publicly, so you can go and and analyze the data and look for possible signs of these elephants trapped in the earth, which we did, and others have done also. So it's an interesting direction. Okay, so if we are now talking a little bit about this idea of scalar fields, oscillating scalar fields, effectively looking like oscillation of fundamental constants, which affects clocks of different types. We can ask ourselves, what if the clocks are normally very, very slow. If they take give you a point sort of every few seconds, this is already considered a fast rate for very precise atomic clocks. And the question is, what if we want to look in the megahertz range, for example, or faster? What do you do? And so we proposed recently to do this with atomic spectroscopy, and the idea is based simply on the fact that if you have an atomic or molecular transition and the fundamental constants are changing, then the energy of the atomic or molecular transition will be oscillating in time. And if you have an optical cavity, for example, then the length of the cavity will also follow. But it is important to understand that there are different time scales. So first of all, different kinds of devices have different dependence on different constants. And second of all, for example, an optical cavity, even if fundamental constants change the Bohr radius with some rate, the perturbation cannot really spread instantaneously over the cavity, and in fact, it's kind of like a low-pass filter. So for high frequencies, the cavity cannot really respond because perturbations cannot propagate faster than the speed of sound. And so when you realize that, then you can make a very simple, this looks a bit complicated of a diagram, but it's actually a simple, in this case, polarization spectroscopy, Doppler-free spectroscopy experiment. And it turns out that you can reach the level of delta nu over nu of 10 to minus 18 in a pretty straightforward way. And so there are now many experiments that are pursuing this route. I would like to mention one recent search for bosonic dark matter that I'm particularly excited about. And this one is using antimatter as a probe. So specifically, this is a work done with the base collaboration at CERN, and their business is to trap individual or maybe a couple of antiprotons in precision traps, in the panning trap, and keeping them there for months and doing very sensitive experiments. So if there is dark matter background that couples to the spin, it should perturb the motion of the spins in this trap, and so the data accumulated over a long time by the base experiment were analyzed to look for dark matter effects. Now, if you compare the sensitivity of this experiment, which I think is really the first, well, you can argue about it, but certainly the first of a kind search for dark matter effect using an antimatter probe. So, and you might say, well, maybe we don't expect antimatter to have any special directing any differently with dark matter compared to normal matter, but there are in fact paradigms that are not particularly exotic that allow you very strong asymmetry in the interactions between matter and dark matter and antimatter. And dark matter, for instance, I mentioned the axion quark nuggets, and they would have 100% difference in interaction with matter and antimatter. So it's possible, and this opens a door sort of in a very interesting unexplored direction. So I'm very excited about this. Okay, so actually, all of these things I have presented here have recently published results, and there is a bibliography that follows in one of the slides that you can then see if you like. But there are now proposals of where to take this further, and I'm quite excited about using levitated magnet, a bit of a unusual, non-obvious system as a system to do sensitive magnetic field measurements and searching for these exotic fields as well. Okay, let me just show you real quick. I'm not have about 5 minutes left. So this is like a little movie that I promised showing you our Gnome network in 2017. So we have fallen into this unfortunate situation that I think is kind of common for high energy physics, where we take data and we have results only significantly later, because it turns out that data analysis is a major bottleneck. It's much harder to analyze the data than do an experiment. So we just published the database, the analysis of the 2017 run. So these are the stations that have participated, and the Earth is moving in the galactic frame, so there is a preferred velocity. So we in fact expect the main walls to come from one particular direction. That's the direction of the Cygnus in the sky. And each of the magnetometers actually has a sensitive direction for the gradient of the axion field. Now if this dark matter, the main wall, is coming through, then you can see that we expect a particular pattern of signals in different stations. That is again. All right. Okay, let me, I have a couple minutes left, so I'd like to quickly mention a few things to you. So,
you have 3 minutes.
Yeah, thank you. Yes, I see. I would like to say that these searches for exotic interactions are going on different scales. And here are some experiments that in principle can be taken down to the atomic scale. And I'm actually, these are not experiments I'm partaking, these are our colleagues, again, at the Institute of Science and Technology in Hefei, and they look single nitrogen vacancy centers, color sensors in diamond. And I must say that you should probably think about this. So if there is some boson, like an axion, for example, which kind of fifth forces can such a particle generate? And there have been catalogs. It goes back to the work of Moody and Wilczek from the 80s. And then there was a catalog that was compiled by Dabresko and Moschow. It's used till today. It's a very nice catalog of possible potentials induced by these particles, but there were some issues, some slight errors and some incompletenesses in this. And so this question of the catalog of potentials has been recently revisited in this paper. And anyway, these are still the Dabresko-Moschow potentials, and the colleagues at USTC have done experiments making significant contributions in limiting the parameter space. And I would like to mention that, interestingly, recently they are in fact seeing some non-zero effects that they cannot explain with the known systematics. My personal take is that it's a bit too early to get excited about the discovery of two different new axions, because I think there is more to explore in systematics. But at least this illustrates that this this kind of experimental platform is very interesting and something to watch. So now let's see. I probably don't have time to tell you about these levitating magnets unless you have questions. I'll be happy to tell you, and also about the plans to deploy them on satellite missions. And okay, this is now my timer is going on. And in fact, just maybe I'll end by saying that there is a lot of work going on, which is I call the couch physics, if you like. It's where you can take precision data, for instance, in atomic spectroscopy experiments, and then you can take this catalog of potentials, and then you can calculate the expected effect of each of these potentials, and then you can see what the difference is, and you can try to attribute it to this exotic physics. And this is a very nice way to limit the different interactions. And so this is an ongoing project with many interesting results, including, for instance, semi-leptonic interactions involving antimatter using antiprotonic helium spectroscopy. And just the very last thing I'm going to mention, that along these lines, several years ago, Gilad Perez and company have suggested to look at the isotope shift in atomic transitions to look for these exotic kind of bosons. And this is done experimentally through measurement of nonlinearities in isotope shift in plotted in a particular way. It's called a king plot. Again, I can tell you in more details about this. And this is a very exciting direction. And our group has been also recently measuring isotope shifts with high precision. The nonlinearities are seen, and so now there is a lot of excitement to understand whether these are some kind of higher order standard model effects, or indeed some new physics, so to say. Yeah, I'm done. I just want to say that I showed you a lot of cartoons, but as I already said, there are papers associated with everything here. And I thank you so much for your attention, and I'll be very happy to entertain questions.
Thank you very much for a nice talk. So any questions from the floor? Okay, you have introduced many different methods for searching for the bosonic dark matter. So what do you think has the best chance for observing the dark matter? I mean, your personal opinion.
Yeah, it's impossible to say because I think the possibilities are wide. So we are searching for dark matter from hundreds of GeV, or even you know, even up to some fraction of a gram in case of quark nuggets, let's say, all the way to 10 to minus 22 electron volt. This is like the lightest dark matter that can be confined in the galaxy. So the parameter space is huge. The couplings could be different. So there's a whole lot of variety. And I should say, there are still also attempts to do away with dark matter and have some other explanations for what we are seeing. It's very, very hard to predict, but I think what is clear, more or less, that we have so many problems now that I feel that we are on the verge of some discovery. Where it's going to come, I don't know. So it's interesting. I think this is one case to argue for diversity and looking for different kinds of things.
Thank you for the wise answer for my stupid question. Anyway, yeah, I agree with you that diversity is important. Any other questions or comments? Okay, if not, let's thank Professor Booker. Thank you very much for a nice talk.
Okay. Let's see, how can I?
Yeah, you can just stop sharing.
Yeah, I'm trying to get to that. I'm sorry, 1 second. I'm trying to. It's okay. Good.
Thank you. Okay, so next in this session is Professor Gagan Mohanty from Tata Institute. He'll talk about latest results from Bell and Bell 2. So,
can you see my screen?
Yes, so you can make it full screen.
Sure.
And
then, let me, yeah. Okay, good, very good. So, yes, good afternoon, good evening. In the next half an hour or so, I will give a glimpse of the latest result from Bell and Bell 2 experiment. It would have been lovely to visit Korea once again, but maybe I look forward to the next opportunity. So just to start with, what is the ethos of this PASCOS series? As I understand, this is a conference of particle physics, string theory, and cosmology. The result that I will be talking about has to deal with these broad themes, specifically on the CP violation within the standard model and searches for new sources of CP violation. Results on the rare and forbidden decays of various mesons. This is an indirect probe of new physics. And then, more on the dark matter, we just heard from the previous speaker, very nice talk of different probes, how it's used. Similarly, in Bell and Bell 2, this is a collider-based experiment, but here also we can, a relatively low energy collider experiment, we can also probe a dark matter, dark sector. Okay, so let me introduce the past generation flavor factory experiment. We had two of them, one Bell at KGB, Japan, and Babar experiment at PEP2 Stanford. Both of them, here you see the kind of the data they have collected. Bell stopped taking data 10 years ago, more than 10 years ago, though the physics harvesting phase still continues. Just to give an example, it has published several number of paper since last year, like 2 PRL, 4 JHEP, and 15 PRD paper. So I'm not going to talk about all of those results, but I will select a portional few. Those are based with the full data sample. So here you see a picture of Bell detector, which is no more there. Obviously, we are analyzing the data. If you want to see more detail about the publication list, please follow this virtual link provided here. Okay, now I move on to the next generation of flavor factory, namely Super KGB, where our plan is to, the Super KGB plans to deliver collision, E plus E minus collision at an instantaneous luminosity of 6.5, 10 to the power 35 centimeter per centimeter square per second, which is 30 times than that of KGB. And how do you get this 30 times more luminosity? You like to increase the beam current that appears in the numerator of the expression by 1.5 times, and you want to squeeze the beam size by 15 times. So that product of the two is the 30 times. So how far we have reached in this pursuit? We have already reached 2.96 into 10 to the power 34, which is already a world record, but then we have some way to go. Just to see a cartoon of the beam profile, that how the electron positron beams look like at the collision point. Here this low energy ring is positron, that is in green, and the red part is the electron beam. So this is what it looked like a kind of two pancake colliding at the interaction point in KGB. And on the other hand, if you go to Super KGB, we're squeezing the beam size. As you see, the beam size is reduced, and then you see that how the thing has changed. So here is in the left-hand side, you see this the layout of the Super KGP collider, and the Bell 2 detector is placed here. Bell 2 has already recorded about 190 inverse femto 1 data, and the results that I will be presenting will be based on something of 70 inverse femto 1 data. The interesting fact is that despite the COVID-19 pandemic, the data taking continues. So we are in fact taking shift, sitting in India, Europe, US, and everywhere. So this is really interesting working model. So let me move on to Bell 2 experiment to introduce to you. This is obviously like a significant upgrade of Bell detector. Particularly, the most important part is the, I'll just say the vortex detector, which is sort of the heart of the experiment. Here we have 2 layers of pixel and 4 layer of silicon microstrip, so-called PXD and SVD detector, followed by gas-based detector of central deep chamber, essentially used for measuring the momentum and charge of the charged particle, then followed by this particle identification device, mostly based on the Cherenkov technique. We have time of propagation counter in the barrel region, and the proximity focusing aerosol region, the end cap forward region. And then followed by the electromagnetic calorimeter. Here we are reusing this cesium iodide thallium doped crystals from Bell, although the readout has been replaced with waveform sampling readout. So these are sort of more optimized for data taking because our data taking is much higher compared to Bell. So these readouts are quite appropriate for that. Then we have the solenoid magnet, and followed by the outside the solenoid magnet, we have so-called the K-long muon detector, where you use RPC and plastic scintillator, first 2 layer RPC followed by the plastic scintillator, and then in the inner layer plastic scintillator, and then outer layer RPC, and in the end cap we have plastic scintillators. This is mostly to do with the radiation. Okay, so let me move on to some results. First one, I start with the Bell. So this is the search for new CP violation in this B23K sort decay mode. This analysis was performed by a Korean student, Kyokyun Kang, from Kyungpook University. So this channel is very interesting. You have, there is a kind of loop diagram, B2S loop diagram, where you can have potential new physics contribution, and that will affect the time-dependent decay rate, right? So there are 2 terms you see. There is a sinusoidal term and there is a cosine term. The coefficient of the sinusoidal term is so-called the mixing-induced CP violation. Because you can have potential new physics, that will make this S term to be different compared to what you have the so-called tree-level B2 CC bar S transition, which acts as like a standard model candle. You can also have within the standard model, A is supposed to be 0 for this decay, but that can also differ from 0 if you have new physics. What you see in this plot, that and in this box over here, rectangular box over here, we measure the sine term or the S term to be given here, and which is deviating from 0 at 2.5 sigma. So this is a non-zero, it's a significant measurement. And the A value, which is supposed to be 0 in the standard model, is consistent with the 0 with this uncertainty of 0.16 plus minus 0.05. So the S value that is consistent with the world average, current world average of sine 2 pi 1. So this is the famous discovery by Bell and Babur experiment, which led to sort of half of the Nobel Prize to Professor Kobayashi and Masukawa. So that is consistent with that sine 2 pi 1 value, as well as its indirect inferred value. And our measurement is more precise than the previous Bell result and consistent with Babur. Just to note you that earlier there was about 1.6 gram discrepancy between the 2 experiments. Okay, so now I move on to another B2 SSS bar mediated decay. So this is, you can see this decay channel B2 pi pi K. you can also have, so this is a penguin decay, but then you can also have a tree decay, B2 eta ck, where eta c decays to 5 So the final state is 5 Now, by having this kind of two competing decay, just if you take a standard model, you do not expect to see any CP asymmetry, but you can have some new physics appearing in this loop, and that would lead to a potential direct CP asymmetry to the level of 40%. This as proposed by Hajime paper here. So what Bell has measured using the full data statistics you see here, we have measured the branching fraction and the CP asymmetry in two regions. First, we measure below the eta C threshold given by this expression, and you see the measurement provided here for the charged B mode and the CP asymmetry for the charged B mode, which is consistent with 0, with an uncertainty of 11%. Now, the interesting part is because we want to see the eta C region, so there we have measured the CP asymmetry, and that is consistent with 0 with a uncertainty of 12%. Okay, so this we have measured the branching fraction both for the charged mode as well as for the neutral mode as given here, and both the branching fraction values were consistent with the theory prediction that given in this particular range. Okay, so now we move on to CP evaluation in the charm sector, where it is expected to be very small, something of the order of 10 to the power minus 3 or smaller. Here, you expect largest effect in the so-called singly Cabibbo suppressed decay because the contribution from the penguin diagram. You also have so-called the Cabibbo favor decay, which proceed entirely by the tree level amplitude. So there, non-zero CP asymmetry is really like a sort of smoking gun signal for new physics. So motivated by that, Bell has measured the branching fraction and CP asymmetry in two SCS decay given here. D sub is going to K plus pi 0 or K plus eta, as well as the Cabibbo favor decay. D sub is going to pi plus eta. We reconstruct D sub s either directly through their final state, or we also look for the so-called the excited D sub s star plus going to D sub s gamma. So that we call it tagged decay and tag sample. And if we are directly reconstructing, that is on tagged sample. And we use this Cabibbo favor D sub s to 5 pi as the reference channel. Okay, so here is the measurement summarized in this rectangular table for the CP asymmetry. So you can see they are consistent with 0. For example, in the Cabibbo, singly Cabibbo suppressed mode, we achieve a precision up to 4% or 2%. In the Cabibbo favored mode, we have further improved the precision, something like 0.3%, little above than that. These are the most precise result and significantly improve our understanding and significantly improve on our current world average value. So this we have also measured the branching fraction. So here you see there are obviously the central value, the first error statistical systematic, and the third error is coming due to the reference channel and other external input that is used. So this branching fraction and CP asymmetry result can be used to test the so-called the sum rule, and which in turn can be used to make stringent prediction for CP evaluation in the charm decay. Okay, so now let me move on to another story. This is there is this famous delta ACP saga, and we would like to rekindle that with Bell too. What is this delta ACP story? That there is a significant difference in the CP asymmetry between two related decay, namely B0 going to K plus pi minus and B plus going to K plus pi 0. Now, these decays are hadronic decays, so there is large hadronic uncertainty. So Grunau in this paper has proposed an isospin sum rule, which essentially link the CP asymmetry and branching fraction of the related B2K pi decay. And this IK pi is supposed to be 0 within the standard model. So by precisely testing this isospin sum rule, which is supposed to be null in the limit of isospin symmetry, and there is no electroweak penguin contribution, so we can see that how much it deviates from 0. And if that it will deviate from 0 significantly, that would be evidence for new physics. Towards that goal, Bell 2 has performed measurement of branching fraction and CP asymmetry for these two decay, B plus to K plus pi 0 and B plus to pi plus pi 0. So here is the measured branching fraction as well as the CP asymmetry. So right now you can see the dominant, we're mostly dominated by statistical uncertainty. Of course, in this case, you see systematic uncertainty is quite large, 1.6. So basically this systematic uncertainty coming largely due to pi 0 reconstruction efficiency, and we have mean to control on that. So it will definitely more improve, and will also improve the statistical uncertainty as we add on more data. Okay, so for that isospin asymmetry sum rule that you see, this so-called IK pi relation, you see there is this K0 pi 0. So that's the most challenging channel. Why is that? Because there are several experimental challenges to measure this K0 pi 0 final state. First of all, you have a pi 0 in the final state that lead to tail in the so-called the energy difference distribution. As you see here, you can see there is a larger tail on the left-hand side. Because of the pi 0, there is a energy leakage. The other challenge is it is a CP eigenstate, so you need flavor tagging, which will also have its own finite efficiency factor. The other interesting thing or challenging thing is the K-sort is it flies certain distance before decaying, so that has its own challenge for the time dependent CP violation study. So using the data of 65 inverse femtobarn, close to that, Bell 2 has found about 50 B0 to K-sort pi 0 decay candidate and measure this branching fraction and CP asymmetry given here. So here you see this projection in the so-called the delta E that I already explained, so-called energy difference in the B meson, reconstructed B meson, and the beam energy that is supposed to peak at 0 for signal. And the background is supposed to be flat largely. And then you have the so-called beam energy constraint mass, or MBC, where the signal is supposed to peak around this nominal beam meson mass, which is 5.28 GeV by C square. And the background is supposed to be kind of kinematic threshold distribution. Now we are here right now in the so-called the CP, the sensitivity to the direct CP asymmetry for K0 pi 0. We have reached up to here, but then we need to go down as we will have more and more data. So because you see here, the most of the uncertainty is largely dominated by the statistical uncertainty, right? Because systematic is just 0.04. So as we accumulate more and more data, we will really pin down this delta A K0 pi 0, and that in turn will help you to more precisely test this isospin sum rule. Okay, so what is the final goal? We can say that current status of the sum rule and the future. First of all, we expect Bell to be a crucial player in resolving the so-called K-pi puzzle. You can get that proof here. You can see the projected uncertainty on this IK-pi without Bell 2. And now you see Bell 2 coming into play, that how that sensitivity is substantially improving. Within Bell 2 even, the direct CP asymmetry for B0 to K-sort pi 0 will be the key. So you can see the importance of B0 to K-sort pi 0 decay channel. Now let me move on to the sort of the third thematic subject. So this is, we have this number of flavor anomalies. Let, for example, this lepton flavor universality ratio, RK star. There used to be this D0 like dimuon charge asymmetry. There is a similar RD star in the semi-leptonic B channel, and there are several other. Okay, and now we also have, well, G-2 of the muon, and so on and so forth. So we have a number of anomalies, and most of them related to muon. So of course, none of them have been convincingly, above 5 sigma or something, and we can close the shop saying that this is it. So these kind of anomaly need to be tested with more data to make sure they are really, sign for something else beyond standard model or just statistical fluctuation. So towards that goal, Bell has measured this so-called LFU ratio, lepton flavor universality ratio, by taking the ratio of the branching fraction of B to K star mu mu and to B2 K star EE, where K star plus is reconstructed in this 2 decay channel and K star 0 is reconstructed in K plus pi minus and K star pi 0. So what is so important about this RK star ratio? These are theoretically clean observable because most of the form factor related uncertainty cancel out. Just to give a scale, you have uncertainty of 10 to the power minus 4 or lower than that. So Bell has measured the RK star in number of Q square bin, including the one up to the highest Q square bin. And that's something unique for Bell, and also will be Bell too. The other interesting thing, let's say compared to LSCB, that for E plus E minus flavor factory experiment, we have similar performance for both for the electron and muon channel. So this, because of the low energy environment and clean environment, you can see similar sensitivity in the electron and muon mode. For example, we get about 100 event in electron and 140 event in the muon in this, as you see in this projection of beam energy constant mass. Now, what is the result and how does how do they compare with the current state of the art? So here you see our projection, result of RK star 0 and RK star plus. So this is the first measurement of RK star plus, which is consistent with standard model. In RK star is also consistent with standard model. However, if you look at the Q square bin, lowest Q square bin, where LSCB reports an RK star value differing from standard model by 2.5 sigma, our is also going in the same direction, but I will not sort of say that we should jump over the because this is having large uncertainty. So this is something Bell 2 will really do well. Now I move on to the related LFU or lepton flavor universality ratio in RK. So this is the ratio of B to K mu mu versus B to KE is in similar number of bin. We have also measured the CP averaged isospin asymmetry, which is essentially the ratio of the charged to the neutral beam measurement decay in the specific lepton channel, be it muon, be it electron. So we have performed a multidimensional fit. Here you see the projection in one of the dimension, namely beam energy constant mass, very clear signal, though not many, but yes. And these are the background. So we measure the Q square RK as a function of Q square. And this is actually the combination of RK star, RK plus and RK 0. So we are largely, our result agree with the standard model. And this red marker, the red marker is the bin of interest. This is where LSCB has got about 2.5 sigma. So our is slightly above LSCB value and consistent with 1. So that is the standard model prediction. In a sense, we differ from LSCB by 1.6 sigma, not a big deal with the large uncertainty we have. What we find very interesting that in this so-called isospin asymmetry, we see the result consistent with null asymmetry. All right, so you see it's all consistently down 0 level, with the largest difference appearing in the same Q square bin where LSCB sees, the RK to be 2.5 sigma below the standard model. We see the AI to be lower than the standard model prediction, which is supposed to be 0, by the way. Okay, so what does future hold for this lepton flavor universality test? So here I show a table taken from so-called the physics of B factory book, Bell 2 physics book as published in this paper, PTAP paper. So here you see different projection. So this is what Bell has already measured, and the projection taking that different luminosity scenario with 5 atoban inverse and 50 atoban inverse. At 5 atoban inverse, we will reach up to 10% uncertainty. And when you go to the full data luminosity, we can go up to something like 3 to 4% uncertainty. So using more data, we can reduce, substantially squeeze the start uncertainty as well as some part of the systematic uncertainty. Now, as I said in the previous slide, Bell 2 has a complementary setup with respect to LSCB. Number one, we have similar performance for electron and muon channel. We can do inclusive channel measurement that will be difficult for LSCB, and also we can do the high Q square part. So while we have a long way to go because the luminosity we have not much, but still Bell 2 has made a beginning by rediscovering one of the related decay channel, namely B plus to K plus L minus, as you see. Not a huge signal, but yes, we are on the right track. And here in this plot, basically you see that what impact the Bell 2 will bring in as we accumulate more and more data in terms of the projected uncertainty in this RK star. So I think the community is really looking forward to Bell 2 result in this RK star ratio. Really in very interesting and in very really anxious to learn more from Bell 2. Let me change the topic. Now look for, it's a related channel. So this is B plus to K plus nu bar. This is a suppressed efficiency decay. And as you see for the K star LL or K LL, there you had photon mediated penguin. You don't have the photon mediated penguin here. So this is really complementary. You have only Z mediated penguin, or you have the so-called the box diagram. So this decay provides a complementary probe to the new physics scenario. Those are proposed to explain the flavor anomaly. Namely, you have lepton quark, you have axion or dark matter particle. Experimentally, this is very challenging. Why is that? Because you have two neutrinos, okay? But thanks to the clean environment of E plus E minus environment, we can use this, this quantum copious production of BB bar, quantum correlated production of BB bar. So E plus E minus going to epsilon 4s to BB bar. So we can use the information of the recoil B. So the B, which is we are reconstructing as signal, that goes to K plus nu bar, but the other B goes to anything. So we can reconstruct that other B meson, and for that we use this innovative inclusive tagging method. And because of the tagging method, we have got a substantially larger efficiency, 4%, compared to, it was much less than 1% for the earlier approach used by Bell and Babar. Obviously, we get a higher background level, but that we fight it out using this machine learning technique called boosted decision tree. And we use two of them, of which the second one is nested boosted decision tree. And by doing that, you see, this is what we have achieved. Here is the projection in the transverse momentum of the lone kaon in the final state here, B plus going to K plus nu bar, and you see the signal here. So here we do not see a significant signal, and we set an upper limit. The expected upper limit is 2.3 10 to the minus 5, and the observed upper limit is slightly on higher side because there is a slight excess, as you can see, that's 4.1 10 to the power minus 5. But obviously, we need to go down somewhere here. That is the standard model expectation. So this result has been submitted to physical review later. Okay, now I move on to the fourth topic, namely the tau sector. The first one I take up is the lepton flavor violation in tau decay. Obviously, lepton flavor violation has already been seen in the neutrino oscillation, but then what is the implication for the charged lepton sector? So, even incorporating the lepton flavor, the neutrino, massive neutrino to the theory, to the standard model, the branching fraction for this decay will be very, very small, really negligible beyond the experimental sensitivity of the B factory. But there are many beyond standard model theory.
3 minutes left.
Sure, I will try to finish it up. Excuse me. Yes. So Bell has done significant, so there is a number of new physics model in which the branching fraction can substantially be larger. So Bell has introduced significant improvement in the analysis by these different, I see these three things I have listed here, and performed an unbeam maximum likelihood fit to the so-called beam energy constraint mass, which is supposed to peak at nominal tau meson mass, and delta E upon root S, which is supposed to peak at 0 for signal. So this ellipse tells you the signal box. And in that signal box, we see 5 candidates, both in muon channel and the electron channel. Those are consistent with the standard model background prediction, as you see in this table. So because of that, we set an upper limit in this range, 5 into 10 to the minus 8, 4.9 into 10 to the minus 8 to be precise, and 6.4 into 10 to the minus 8 for the electron channel. So these limits are more stringent. So these are the expected limit. These are more stringent than vapor. Observed limit side, we get 4.2 and 5.6 10 to the power minus 8. And muon channel, we have got the most stringent result. So that's about the lepton flavor violation. What about baryon number violation? Tau is the only lepton that can decay to hadron. So we have searched for several baryon number violating decay. As you see here, we haven't found, unfortunately, this signal, but we set upper limit. And here in this canvas, you see the result of Bell, new result, which are given by this blue diamond compared to the existing result. Okay. Now, what can Bell 2 do here? You can see again these limits from different experiments, including experiment result from Atlas and CMS. Okay, they can only do for tau to 3 muon. And you see we have reached up to the 10 to the power minus 8 range. And in Bell 2, we can push it to at least 2 order of magnitude to 10 to the power minus 10 or even lower in some case. Okay, so just I'll take 1 minute. So this is about dark sector. I know there is a dedicated talk, but then the student from Professor Kyon's student Sokhi did this analysis for dark photon search. So here basically he looked at the B meson decay to a pair of dark photon and subsequently decaying to 2 lepton, opposite charged lepton or pion, and he didn't find any signal in this mass range of 0.01 to 2.62. That is basically half of the B meson mass, and set the upper limit given here of the product of branching fraction. And from that upper limit, he also calculated a upper limit on the Higgs boson coupling for each assumed A prime to H prime mass. Okay, so I don't want to talk about this thing because this is already presented by Sabino on last Tuesday. Just to say that the past 2 highlighted results from Bell 2, those are published from to PRL, is on this dark sector. So this is kind of the concluding, the main 2 plot. And so I would like to conclude just to say that despite passing the pattern of the frontier flavor factory experiment from Bell to Bell 2, we continue at Bell. We continue to produce exciting physics results, and we'll do so until Bell 2 integrates similar data as Bell has. And our agenda, for Bell 1 phase, it was for the CP violation and the sort of proving the Kobayashi-Mascow paradigm. But for Bell 2 and the kind of analysis that we are doing Bell right now with the Bell data is to probe new physics indirectly. So this is really complementary to high PT program of Atlas and CMS at LSCB at LSC. But then obviously we need to have more data, particularly for these flavor anomalies and things like that. So let's keep watching, and we shouldn't give it up. Thank you very much.
Thank you very much for a very nice summary. So any questions or comments?
Yeah, I see one from
Dimitri. So
yes,
you can
please.
say.
Yeah, thanks so much for the talk. I was curious about the time-dependent CP violation studies. Can you speak a bit more about that?
Right. So what happens? We have very clean. So you have E plus E minus going to epsilon 4s, and which decays almost 100% of the time to the BB bar. And here we talk of the neutral B meson, and so sort of one B meson is going to this 3K sort. So this is a CP. This is a CP eigenstate. So you cannot know whether it's a B0 or B0 bar, right? Because from the final state, you cannot know that. So we use the so-called the information of the recoil B, the tag that we call tag B. Actually, I should have a cartoon for that. So we measure the delta T. So this is the proper time difference between the recoil B meson or tag B meson and the reconstructed B, that is what we call signal B. All right. So and the thing is, for all good reason, the B factory are asymmetric energy. So these are not the, so why is that? Because your center of mass system is no more at rest. It is going in certain direction. So B and B bar are decaying at different time. So there is a appreciable decay flight length between them. So from that we measure delta T. Now, if there is no CP violation, what you will see, the red and blue will be one top of each other. The fact you see the two of them are away, and in fact you turn to a sinusoidal translation and excuse me, and so that is number one, that why you have S term non-zero. So that is basically the difference, the red and blue, they are not on top of each other. Now the height difference, if there is a height difference between red and blue, that is direct CP violation, and there we see it is consistent with 0 basically. So yes, we measure the decay time difference between the B and B measure, and from that we do that, and this is what we measure. And now question is, what I said, new physics, that you are supposed to, so this is so-called the penguin decay or quantum loop decay, right? This we compare with so-called the tree decay, where you have just B to C transition, right? So in the tree decay, it is very difficult to appreciate large CP, large new physics contribution. Here you see there's a potential new physics because of the loop, uncertainty principle. So you want to compare the CP asymmetry with the tree dominated CP asymmetry, and we see they are consistent. So that's, if I can say once again.
Thanks so much.
Okay, any other questions? Okay, can you go back to page 11? Maybe I have a small question. I mean,
sure.
Very minor question.
Sure.
So
sure.
When do you think BEL2 can make some impact in the isospin test? I mean, the summary test. Yeah.
Right. So as you know that by long shutdown next year, we will have sort of data similar like Babur or Bell, right? So at that stage we reach somewhere here, but that's not enough. So to me, in order to reach a few percent, right? So that will be something you are talking of middle of 2020, something around 2024 or 20. So after long shutdown, when we kind of reconvene and 1 or 2 year of data, assuming we are going at the higher luminosity, so that's the time I would say. I mean, once you reach a precision of something 0.05, okay, so then you see it kind of taper down.
Okay, so maybe PASCOS 2025.
Yes. Yeah.
Okay. I guess everyone wants to have dinner before coming back for the public talk. So if there is no urgent question, let's adjourn the session. Thank you, Dimitri.
Thank you very much. Have a very good dinner.
So this session is adjourned now.
Right.